In this short video, we're going to explore the net change theorem. What do we mean by net change? Net has this notion of you would take the initial state and compare it to the final state, and you don't really care what happened in between. So for example, if you take 3 steps forward and then took 5 steps back, well, you did take a total of 8 steps, but your net change is 2 steps backwards. You are 2 steps backwards from your initial position when you finish taking your steps. Another example is the temperature rises 30 degrees, then drops 10 degrees. So you had 40 degrees of changes, 30 up, 10 down, but the net change is an increase of 20 degrees. From your beginning temperature to your final temperature, the net change is going up 20 degrees. So how does this apply to integrals? Well, we know that displacement is the antiderivative of velocity. So what if we had a definite integral of the velocity? What would that represent? Well, using the fundamental theorem, we know that that would represent the position function evaluated between time equals a and time equals b, which would just be the position at time equals b, subtract off the position at time equals a. So here is my final position, and I'm subtracting off my initial position. And that is our net change in position from time t equals a to t equals b. So the net change theorem says that the integral of a rate of change is the net change. That is, if the integrand represents a rate of change of some quantity, the integral itself will be the net change in that quantity. So we already saw that if the integrand is the rate of change of position, the velocity, then the integral is the net change in position. Another example would be if the integrand is, say, fuel consumption rate, then the integral is the net change in the amount of fuel. Let's look at some examples. If the function lowercase f of x is the slope of a trail at a horizontal distance x miles from the start of the trail, what does the definite integral from 3 to 5 of f of x dx represent? Well, the slope is my dy dx. And in fact, so that would be the elevation. Y would be the elevation. So dy dx would be the rate of change in elevation, which is the slope. And I'm going to use uppercase F because uppercase F will be the antiderivative of lowercase f to represent the elevation. So our definite integral can be written as the definite integral from 3 to 5 of uppercase f prime of x dx, which from the fundamental theorem will just be uppercase f evaluated when x equals 5, and then subtract off uppercase f evaluated when x equals 3. Well, uppercase F, we said, is the elevation of the trail, x miles from the start. So this would be the uppercase F of 5 would be the elevation of the trail 5 miles from the start. And uppercase F evaluated at x equals 3 would be the elevation of the trail 3 miles from the start. So this is just the change, the net change in elevation. So bear in mind that maybe the trail goes up and down. It may go, down into a valley, then come back up. But that doesn't matter for the net change. What matters for the net change is what is the elevation 5 miles from the start? What is the elevation 3 miles from the start? Our next example, we have a particle moving in a straight line, and it has a velocity of t squared minus t minus 6 between t equals 1 and t equals 4. What we'd like to do is calculate two things. We'd like to calculate the change in position, meaning the net change in position, from that t equals 1 to t equals 4. And we'd also like to know what is the total distance traveled during that time frame. So it'll be useful to draw a graph of the velocity function. And it's a parabola. And so it's negative from t equals 1 to t equals 3, and then it becomes positive. So in other words, it's moving to the left originally. That's what the negative sign tells us. And then it stops when t equals 3 and starts moving to the right. And so the question is, in the end, am I going to be back where I started, a little bit to the left or a little bit to the right? Well, let's go ahead and evaluate that integral from t equals 1 to t equals 4. Find our antiderivative, evaluate it between 1 and 4. So let me first substitute the 4 into my antiderivative, then subtract off the quantity I get when I put in 1 in the antiderivative. And if I did my arithmetic correctly, that's going to be negative 9/2. So the negative is telling us that I am to the left of where I originally started. So at time t equals 4, the particle was 4.5 units, so that's 9/2, 4.5 units to the left of where it was at time t equals 1. So that's our net change. What about the total distance traveled? Because we stopped and came back a little bit. So let's find out first how far we moved to the left. That's when v is negative. So I will calculate the definite integral from 1 to 3 of the velocity. That'll tell me the distance moved to the left. So same antiderivative. Now perform the evaluation between 1 and 3. And I'll get negative 22 over 3. So it moved a total of 7 1/3 units to the left, and then it stopped. Then it started moving to the right. That's when v is positive. So we're moving to the right. Let's evaluate the definite integral from 3 to 4 of the velocity function. Same steps, we'll find the antiderivative. Now perform the evaluation from 3 to 4, and I get a 17 over 6, positive 17 over 6. So the path of the particle, the journey of the particle, was to start at some position, move to the left, negative 22 over 3 units, stop, then move to the right, 17 over 6 units. So the total distance traveled would be the distance moved to the left plus the distance moved to the right, but without any signs. When we're looking at total distance, we don't care whether we're moving to the left or to the right, so there's no negative sign on the 22/3. So 22/3 plus 17/6 gives me 71/6 units traveled. What if I had kept the negative 22/3? I would wind up with the net change. Negative 22/3 plus 17/6 would be negative 9/2. So when we're looking at total distance traveled, we're really kind of looking at the absolute value of the velocity function and evaluating the integral of the absolute value.